try to determine the mass moment of inertia of a connecting rod. Probably not the exact title of the experiment, but that is what more or less you do. And in the last semester, we also did one experiment where we tried to determine mass moment of inertia and radius of gyration of uh, another mechanical component, which was a flywheel. In some sense, the approach is the same, uh, and in some other sense, it is also very different. So if you think about it, mm, so let's first start by defining the mass moment of inertia. And let's not confuse this with any sort of area moment of inertia. So let's say we have an axis. Let's call it axis uh, A, and let's say we have a particle. Now, no real life object is actually a particle. A particle is something which has no dimension, but in order to make it visible, I'm just drawing a finite circle. And let's say that particle with zero volume apparently has a finite mass, which is m. And that particle is situated at a distance of r from this axis. So this is the smallest distance, the perpendicular distance. If you draw a perpendicular on this line from this point, from this particle, the location of this particle, okay, so that would be this r. So the mass moment of inertia for a single particle is denoted by I and is essentially this quantity. So this is the mass moment of inertia about the axis AA. If it helps, you can put a suffix after I to represent it is about that axis. Now if there are more than one particle, so there is a system of particles, so there is different particles, particle 1, particle 2, particle 3, etc. These are all normal distances. You'll have to imagine in 3D. So in that case, we will simply add the individual mass moment of inertia to get the mass moment of inertia, the net mass moment of inertia about the axis of this system of particles, which basically means the summation basically means m1 r1 squared plus m2 r2 squared and so on. Now imagine if there is a rigid body which is an object of finite dimension, but changes on those dimensions is quite negligible. So all I'm trying to say here is it has negligible strain through the interaction with the surrounding. Thing like that would be a rigid body. A real life object would be called a deformable body. A more realistic approximation of the real life object would be called a deformable body, wherein the body itself has finite dimension, okay, and also it is deformable. Okay, so a rigid body doesn't change if we apply different forces from different directions. And if we have a deformable body under the application of different loads, it would probably deform. Okay. Now, be it a deformable body or a rigid body, for any object for which we are considering the finite dimensions, okay, the definition of mass moment of inertia is something like this. So imagine this is where the axis passes through, same axis A drawn with a blue color, okay, and inside the body, imagine there is this differential mass element, okay, the way we take differential volume element, differential length, okay, like dx, differential area is like dx dy, differential volume is like dx dy dz. You can imagine this differential mass is essentially this differential volume times the density, which may or may not be functions of the coordinate. If it is a homogeneous material, it might as well be a constant. So you take a differential mass, and you also need to take the distance, the normal distance of, so imagine it's a 3D object. Try to have the understanding of the third direction, which is normal to the plane. So this line on a projection might not look like a perpendicular, but it is actually. And that length of that normal is r on the axis. So the definition of the mass moment of inertia with finite dimensions, so both of these has finite dimensions, but for this one, the rigid body, this is negligible strain, there is negligible strain. For deformable body, the strains are finite. So the mass moment of inertia is defined with an integration, which is r squared dm, and that integration you are supposed to perform all over the body. So take different mass elements, differential mass elements everywhere, okay, and for every such mass element, get the r, do r squared, multiply with dm, and add them up. And the fact is, why instead of using a summation, I'm using an integration, because this differential mass element is infinitesimally small. So you are supposed to do an infinite number of such summations. Okay, so that's why it is represented with an integration. Okay, so there you have the definition of the mass moment of inertia. And when you are defining mass moment of inertia for either a system of particles or an object with finite dimension, you can also define something called a radius of gyration. And this line right here is a definition of something called a radius of gyration. This is not the definition of mass moment of inertia, but the definition of radius of gyration. Okay, so basically there could be two objects, one which looks like this cylinder, which has mass, but the mass is not much dispersed from the axis. Whereas I can think of another cylinder with the same mass possibly, but the mass being distributed away from the axis. Okay, just by looking at these two, one can immediately say if they have the same mass, the second object right here is going to have higher mass moment of inertia, because the mass is located further away from the axis as compared to the first body. Okay, and there is a way to effectively represent for any given body its mass being represented like that of a particle, which when situated at a distance from the axis, namely the distance is namely known as the radius of gyration, produces the same mass moment of inertia. So this is a particle of same mass as the actual body with finite dimension. Okay, it has the same mass, and it also has the same mass moment of inertia about the axis A. The only thing is, in the first body, the mass is evenly distributed or maybe unevenly distributed. But in the second case, the mass is concentrated at a point. Okay. So the definition of radius of gyration is that it is that effective radius where if the entire mass of the object were to be concentrated, it would have the same mass moment of inertia as it has with its distribution of mass over finite dimension. Okay. So this is your first assignment question. The first assignment question is define mass moment of inertia for a single particle, system of particles, and object with finite dimensions. Number one. And the second part is define in words what is radius of gyration. Okay. Is this part clear?
Yes, sir.
Yes?
Yes, sir.
Yes, sir.
Okay.
Sir, question ta arekbar bolun?
Yes, sir.
Question. Okay. So the first part of the question is define mass moments of inertia for three different situations where you have a single particle or a system of particles, and the third situation is where the mass where you have a object of finite dimension where the mass is distributed all over the space that it occupies. Okay. So define get the mass moment of inertia for three different situations. Number one. Number two is, the second part of the question is define the radius of gyration in words. Explain the significance of radius of gyration. Okay. Achha, for today's experiment, there is probably no dedicated chapter or reference in the book by Dieter, which would be more suitable to when we are doing some sort of material testing. When we are testing some sort of material properties, say ductility, brittleness, or hardness, or tensile strength, any such thing that we are doing related to material, there the book by Dieter could be helpful. But in this case, there is no reference from that book. So the reference for this experiment you directly get from your textbook. If you open Medium and Craig, the dynamics part, the engineering mechanics dynamics part, so there are two books, one for the statics, the other one for the dynamics. So you are supposed to open the book for dynamics, and there you need to find the chapter on rigid body dynamics firstly, and even in that chapter go for the planar rigid body motion, and in that you are supposed to look into the details of a compound pendulum. Okay, that's exactly the topic that we are looking into.
तो बोइटर नंबर কি বললেন আবার?
Medium and Craig, Engineering Mechanics by Medium and Craig.
আচ্ছা, ওকে স্যার।
স্যার একটা কোশ্চেন ছিল। হ্যালো স্যার।
হ্যাঁ বলো।
স্যার রিজিড বডি মানে পারফেক্টলি কোন রিজিড বডি আর স্ট্রেনটা
তোমার কথাটা পরিষ্কার আসছে না, বলো।
বলছিলাম পারফেক্টলি রিজিড বডির যে স্ট্রেনটা ওটা কি আমরা জিরো কনসিডার করতে পারি?
প্রথম কথা হচ্ছে রিজিড বডি বলে কিছু নেই। The real life objects are deformable bodies. Number two is, just like there is no such thing as particle, real life objects have finite dimension. And also the way we look into deformable bodies, we consider them to be continuum. That means there is no discontinuity. Okay, that is also not true. The material has discontinuities, as in there are ports, there are grain boundaries, there are crystallographic imperfections. Okay, there are voids, there are metal solutions, other things are there. So each of these things are just improved model of the real life objects. So once you go from particle to rigid body, that is an improved modeling of the real life objects. Once you go from calling something a rigid body to a deformable continuum, that is also an improved model of the real life object. But then there is also the microstructure, and there is no end to it. You know that, right? I mean, it's not. Don't take it literally, but you can dig more and more into that, and so all of these are at certain level are helpful models for us to solve any given engineering problem with uh, mm, with reasonable accuracy and not much of a difficulty. Okay, so that's what these are. Number one. So when you are trying to model something as a rigid body, there is no such thing as a rigid body. But when you are trying to model something as a rigid body, you essentially consider the strain to be zero. Okay. Acha.
Okay, sir.
Acha. So now one or two words about So we discussed about mass moment of inertia, but there are two parts to our experiment, right? There is a connecting rod, and we are trying to get its moment of inertia. Now we need to know what is a connecting rod, and for that we need to make ourselves concerned with the 4-bar mechanisms or mechanisms in general. So the two very familiar mechanisms for us are like this 4-bar mechanism. I'm deliberately drawing a crank rocker mechanism. So you can imagine, so this is a crank, this goes full rotation, and this one only oscillates. Okay, so these are 4 links, and every circle that I'm drawing essentially representing a pin joint in itself. Okay, and the ones with 2 circles, or this, the darkened circle, these are actually attached to the ground. Okay. There are several examples of 4-bar linkages. For example, in your engineering drawing courses, you use the drafter, and the drafter uses actually parallelogram linkages. Okay, and they are actually rocker. I say rocker, but theoretically they are actually crank mechanisms. Both sides should be able to rotate, but this is how we use them. What other example of 4-bar linkage? For example, if you take a bus to your workplace, then you know that during this monsoon season, so the bus employs, if you ever get to sit in one of the front row seats, then you will notice there is the wiper of the bus. So the wiper actually acts like this. So the wiping part would be attached to this rocker. Of course, it would be actually inverted. Okay, and the crank is this small link that is attached to a motor. So there you have a motor, and that makes the crank rotate, go full circle, because that's how motors operate, right? The shaft rotates completely. So the crank is attached to the shaft, which goes full rotation, and then there is this rocker, okay, which is basically your wiper, and that just oscillates while this goes full rotation, and this basically wipes the glass of the windscreen of the bus. Okay. Where else you should have seen a crank rocker mechanism? It's so parallelogram linkage is a 4-bar mechanism, and this crank rocker mechanisms are also 4-bar mechanisms. But I want to give you another example of a crank rocker mechanism. Let's say you are riding a cycle. Okay, so this is essentially the 2 parts of your leg. Okay, this is like your thigh, and this is like your the calf portion of your leg. Okay, and then to this is attached your the paddle of the cycle. Okay, which goes full rotation. Okay, because this one goes full rotation is that your wheels are rotating and you are moving forward. Okay, and the 4th linkage is kind of the distance, the fixed distance between your hip and the center of the paddle. Okay, And you need to understand why the paddle must be this small. Because the paddle is small, the paddle acts like a crank, and this portion of your body and also this portion, okay, this one becomes a rocker. So this basically oscillates. So from your hip to your knee, that one only oscillates. That doesn't go full rotation. And this crank goes full rotation and makes the cycle move forward. Okay, and this portion is called a coupler, which basically couples between the crank and the rocker. So this one is the crank, the paddle, and your your thigh becomes the rocker. Okay. Now imagine if I wanted to have more and more mechanical advantage, and I had made the paddle too large in order to have that mechanical advantage, higher moment and all. Okay, what would happen? There is a limit on up to what length this would act like a crank, and beyond that, actually, this other part, okay, that should be the crank. That means your leg must go now full rotation, but in order for you to move the cycle, okay. So that would be impractical, right? That's why the paddle can be only of certain length. So these are the examples of crank rocker mechanism, and there are plenty of examples of crank slider mechanism. Both are 1 degree of freedom mechanisms. So basically there is only 1 degree of freedom, and that is the theta angle of rotation of the crank. So this is what is a crank rocker mechanism. So this part attached to the ground is called a crank, and this is the slider. Okay, and this part is called the connecting rod. Now I am just drawing them. Sorry. I'm just drawing them as sticks, but they of course have their own shapes. Okay. Now, now can you tell me, what happens in this case? As the crank rotates, typically this one is either attached to a motor or to an engine, and when this thing rotates, okay, either to and sorry, this crank is attached to a shaft, which is either driving, which is either driven by your a motor, or it is driving a shaft with mechanical load. Okay. And as it rotates, this portion, this thing can only oscillate. Okay. Meanwhile, the connecting rod performs a combination of the translatory motion and rotary motion. So the crank only rotates, the slider only translates, but the motion of the connecting rod is combination of sliding as well as rotating, which basically means that if I consider that connecting rod, its center of mass is having a translation. Okay, the body itself could also be rotating about the center of mass. Actually, it's not the center of mass which has a translation. It is this point that is attached to the piston that has a pure translation. Okay, pure rectilinear translation. And on top of that, there is rotation, because the crank orientation is also changing. Okay, so together they accomplish the motion of the crank slider mechanism. And can you think of the examples of crank slider mechanism? The obvious example.
Yes.
Yes.
IC engine, sir.
IC engine is the most obvious example, and actually the connecting rod, that the one that we will be using for our experiment, is also supposed to be a part of a IC engine. Okay, so what we have established that that this connecting rod, first of all, it undergoes both translatory and rotary motion. Also, one would have argued that This one only is connected to the two bodies. One is the piston, the other one is the crank, through two pin joints, which would have made it a two force member. Okay, the point being that the force on it would pass through along its length. But that's not the case, because it is not stationary, it is not in equilibrium, it is going through motion. Okay, now this situation would have given the equilibrium, but it is not in equilibrium, it is under motion. So the forces are not along these two lines. Okay, so there are forces, the forces are coming from different directions. Okay, at these two joints they are coming from different directions, and therefore this member right here is subjected to both axial load as well as bending sort of load. Okay, what I'm trying to say here is, if you take this force components, they will have if you take components of these forces, they will have both axial, which is along this line, and also lateral components. Therefore, the member is subjected to uh, uh, both axial loading as well as bending or transverse load. Okay, and therefore the shape of the connecting rod also is also very special. Okay, and this is what the connecting rod more or less looks like. So this part attaches to the piston or the slider, and this part, the larger diameter hole, that attaches to the crankshaft. So which is basically a shaft, but not a simple cylinder. You can imagine if I take some portions out of this, okay, and directly make crank out of it. Okay, so this one is a crankshaft. So in a 2D drawing, it is very easy to show that there is this motor and to which this crank is attached. Okay, but in practice, if you want to have multiple cranks on a single shaft, or even a single crank on the shaft, which is not at one of the ends of the shaft but in the middle, that crank intersects with the shaft axis. And how do you make that? You make that by making the shaft non-existent, physically non-existent, in the portion where there is the crank. So this is what is a crankshaft, and to this cylindrical portion attaches this larger diameter portion of the connecting rod. Okay, and these two parts are actually separable, and they can be joined using once you make it go through the crank, then you can join it using nut and bolt. Okay, so you can fasten them with nut and bolt. Okay, and that's how the assembly works. Okay, uh, now our job here is to um, is to determine the mass moment of inertia of the connecting rod. Okay, now number one is, why do we need to determine the mass moment of inertia? First of all, when the piston is moving, when the shaft is rotating, or rather when the vehicle is running, or when the IC engine is operating, in that situation, the net inertia of the system, okay, is affected by the inertia of the piston, uh, the shaft, the flywheel, which is not shown here, but also that of the connecting rod. So the connecting rod may be rotating or oscillating, but that also becomes a part of the rotary inertia of the system. And how much torque is required to cause to accelerate the system, okay, that would depend on that inertia of the system. So that rotary inertia, um, of course, there is the translatory inertia can be easily determined, okay. So both translatory inertia, which basically means the mass, and the rotary inertia, let's say the mass moment of inertia about the center of mass, okay. So that's why I'm putting a bar over it, which means the center of mass, okay. So which is m r squared as seen from the center of mass. So these two quantities are both important to determine that sort of inertia. Okay. Uh, so mass can be very easily determined, right? So you can place it on a weighing scale and get the mass, but it becomes difficult to identify the mass moment of inertia, and that's what we are trying to do here. Okay, so let me again go through it so that it becomes clear. Why do we need to determine the mass moment of inertia? Because the inertia of the connecting rod, both its translatory inertia and also the rotary inertia, all I'm trying to say here is the mass and the mass moment of inertia, both contribute to the total inertia, total rotary inertia of the system. Okay, and why do I need total rotary inertia? Because the amount of torque required to cause the acceleration, that depends on it. So we need to know the rotary inertia of the system, and for that we need to know the both the mass and the mass moment of inertia of the connecting rod. Okay, if we can know the mass moment of inertia of the connecting rod about its center of gravity, we can determine, or the center of mass, we can determine the mass moment of inertia about any other point. Okay, so we can use something called a parallel axis theorem. Now uh, we talked about two inertias. One is the translatory inertia or the mass, the rotary inertia, which is the mass moment of inertia. The mass can be very easily determined, as we said, using just by weighing the component. But it's the mass moment of inertia that is not very easy to determine. Not for an object which is very irregularly shaped. If it is like a solid cylinder, you can very easily determine how much is the mass moment of inertia. If it is like a plate, okay, thin plate, you can very easily determine the mass moment of inertia. But if it is shaped something like this, which is very irregular in most part, although maybe symmetric about this axis, but it's still difficult to determine the mass moment of inertia from the analytical calculation. From hand calculation, you cannot simply determine it like that. And that's why we are going to do today's experiment to see how we can do that. Now, at the beginning of the class, I mentioned that this experiment in some sense is similar to that of flywheel experiment, and in some other sense it is also different from that experiment. The sense in which it is similar is we are trying to determine the mass moment of inertia of a component, and if you can imagine, the unit of mass moment of inertia is in metric system would be kg meter squared. Okay, and if you recall, in flywheel experiment, we we did an so we what did we do? We hung weight from the shaft, okay, using a rope, and then we let the weight fall, and then the flywheel would accelerate, and then it would decelerate and slow down, and eventually come to rest, and we would measure certain time of of its entire you know uh, dynamic process. Okay, so the measured quantity while you were doing the experiment was time, certain time. Okay, and the unit for that would be second, and from so which is one of the principal units, okay, of the three principal units, which is mass, distance, and time. So you're using second to, if you recall the flywheel experiment. So you noted down some time while doing the experiment, okay, which was in seconds, and from that you try to get the mass moment of inertia, which has the other two principal units. Here also you would measure certain time, okay, and from that time we would actually try to get the mass moment of inertia. And so the this is an interesting thing about this experiment, just like the flywheel test. So you measure certain quantity which is in totally different principal unit, which is in seconds, and eventually you get a derive a quantity out of the experiment which would be in two other principal units. Okay, so and also the similarity between these two experiments ends here. Okay, the dissimilarity is in the process. The processes are entirely different, and we'll come to that process. But but I would do that using by showing you some animation. Okay, so what I did was I created an approximate model in ANSYS to represent the connecting rod. Of course, this doesn't have all those components that we drew, uh, and this actually explained the process. So what I'm trying to do here is taking the connecting rod, and you see this larger circular hole right here. Okay, so this in that larger circular hole, I find the highest point inside the circle, inside the hole, the highest point, and make that as a pivot point. I would place this connecting rod uh, at the highest point of this circular hole, the largest circular hole, on a knife edge. Okay, basically, I would have a knife edge on which I would simply put this connecting rod in this configuration. So automatically, the highest point would be the pivot point, and I would let the connecting rod oscillate about its pivot point. Okay, and while doing the oscillation, I should also be careful that the amplitude of oscillation is quite small, so small that sine theta could be approximated as theta, that small, which is approximately 5 degrees. So the releasing angle, so I would let the connecting rod oscillate about oscillate on its own, or I would go for natural oscillation. We and We would show that if we release it from a very small initial angle, that actually becomes simple harmonic motion. Okay, and while doing that simple harmonic motion, we'll note down the time taken for 10 oscillations. Okay, 10 complete oscillation. For example, if I take the bottom portion towards the left and release from there, so it would come to the central portion, then go to the right portion, that is the opposite side, and then again come to the central portion, and then again come to the left side, and that completes one oscillation. So in this way, I would look for 10 oscillation and note down the time taken for that, and from that I would identify the time period. You see, for example, let's say, okay, one second. Okay, so let's say it is released from extreme right, which is a tiny angle, let's say 5 degrees. Okay, now it would, once released, it would go to the center and then move towards the left, and then once reaching the highest angle or the amplitude in the left, it would again come back to the center, and then again it would come back to the right from and close to the angle from which it was released, and that's when a single oscillation is complete. So this is a simulation of 10 such oscillations. So it goes to the center, goes to the left, and then comes to the center and comes to the right, and that's when there is single oscillation. Okay. So we would do it in two steps. So first, I would make the highest point on the highest point on the larger circular hole as the pivot point. Next, I would invert the connecting rod. Or maybe you can consider this one as the upright configuration and the other one as the inverted configuration. So you would use you would do this experiment with two configurations. Okay, we would oscillate the connecting rod with two configurations. So in the next situation, what we would do is we would make the highest point on the smaller circular hole as the pivot point and let the connecting rod oscillate, and we would note down the time of 10 oscillations. Okay. So because of the shape of the connecting rod, the center of mass would be more closer to the larger circular hole, so compared to the smaller circular hole. And that what I'm trying to say here, that once I get the time taken for 10 oscillations and then divide it with 10 to get the time period of oscillation, the time periods in two different situations, two different configurations are going to be different. Okay, but I need to have I am not saying they are going to be too much different, or they I'm not also saying that if they were not different, we would not be able to do this experiment. I'm not claiming any of that, but all I'm trying to say here is that because of the shape of the geometry, the time period in two configurations would be different. Okay, and it is by doing the getting the time period of oscillation in both the configurations that we would be able to determine the mass moment of inertia of the connecting rod. Okay. Now, of course, you would see the physical version of this simulation in the actual experiment from the recording that I'm about to show you. But the reason I'm showing you this animation is I'm trying to explain the process of the experiment so we can go for the mathematical derivations. এই পার্টটা কি বোঝা গেল যে এক্সপেরিমেন্টটা কিভাবে হবে?
হ্যাঁ স্যার, ওটা তো মানে প্রথমে
না এক্সপ্লেন করতে হবে না, বোঝা গেছে তো, তাহলেই হবে। ওকে, so now we would talk about little bit of theory of oscillation of pendulums. We'd start with a simple pendulum. Of course, the one that we have here is a compound pendulum. What makes a simple pendulum? You have a massless string, an entire mass is concentrated at a point called a bob. That's what makes a simple pendulum. And let's say it is at an angle of theta. Okay. So the two forces that are acting on this particle, which is the bob, is one its weight mg. The other one is coming from the string, which is t. And if we take two axes, so this angle with the vertical is actually theta. Now, if we define two axes, one is the radial direction. Sorry, yes, the other one, normal to that, is the theta direction. So if we sum the forces in theta direction, that would be minus mg sine theta. Okay, so this angle is theta, this much is sine theta, and it is acting opposite to the theta direction, so minus mg sine theta, and that actually is mass times the acceleration in theta direction. Now in polar coordinate system, these are the accelerations in theta direction. There is r theta double dot plus twice r dot theta dot. So this one is a Coriolis component. If you recall your lessons from engineering mechanics, this is the acceleration in theta direction. In radial direction, these are the accelerations, r double dot minus r theta dot squared. But you will have to imagine, in a simple pendulum, the string is unstretchable. Point being that r dot equals 0, r double dot equals 0, which basically means this quantity is 0, and that basically means this is mr theta double dot. Okay. Acha, let's call the length r equals L. So the equation of motion becomes this ml theta double dot, because the radius is always L, equals minus mg sine theta, that is ml theta double dot, or in other words, theta double dot plus g divided by L sine theta equals 0. This is the actual equation of motion of a simple pendulum. Okay, and this one is a ordinary differential equation of second order, but it is a nonlinear ordinary differential equation, and we do not know how to solve a nonlinear ordinary differential equation using analytical method. We can take help of some numerical method, but we do not know how to use that, how to solve that in analytical method. Second order, as in second derivative, is involved. Nonlinear because a nonlinear function of theta is involved. So what we can do is, if we say, and that's why the criteria comes, that if I release theta 0 many times smaller than pi, okay, such that sine theta can be approximated as theta. Literally, we need theta to be that small. We know that that only happens at theta tends to 0. But even if theta is less than 5 degrees, the radian equivalent of 5 degrees, which is 5 pi divided by 180, which would be less than pi by 36. So in that value, if theta releasing angle is less than that, okay, so of course, because it's an ordinary differential equation, of course, but this is an initial value problem. Which basically means, to solve this equation, we would need initial conditions. For example, theta at t equals 0 is theta 0. And let's say theta dot, while released from that initial angle, it would start from rest. So theta dot at t equals 0 equals 0. Those are the initial conditions. Okay. Now imagine, instead of this equation being in time, if this was with respect to the derivatives were with respect to x, a spatial coordinate, that would be a boundary value problem. For example, the equation of a beam EI W double prime equals minus m, that is a boundary value problem. And you need to have the boundary conditions of W. Let's say it's a simply supported beam. So W0 equals 0 and W at L equals 0. Now the problem with time is you cannot know the future. You cannot say at t equal 10 seconds. You cannot say that. You can only provide the initial conditions and hence the initial value problem. Now in that initial value problem, this theta 0, the initial release angle, if that is much smaller than pi, then you can approximate sine theta to theta and your equation in hand becomes a linear ODE. So everything remains same. It's a second order ordinary differential equation, an initial value problem, but this time it is a linear equation. Okay. And we already know the solution to this equation. The solution to this equation is that theta equals theta 0 cos omega n times t, where omega n is the natural frequency and omega n becomes square root of G by L. So this should be important for us. Natural frequency is square root of G by L. You already know how to solve this equation, right? So you can imagine G by L equals m squared, or sorry, minus G by L equals m squared. So you have theta double dot equals m squared theta, which basically means that theta equals C0 e to the power mt plus C1 e to the power minus mt, and this m would be a complex number which is square root of minus G by L, and from that you can actually get a sinusoidal solution. So you should know that. Okay. Now this thing is so this expression. Okay, keep just copy this expression. This is important for us in relation to simple pendulum. The next thing that we discuss is a compound pendulum. So what is a compound pendulum? Whatever is not a simple pendulum, whatever is not a string and a bob, is a compound pendulum. This uniform rod attached to a pivot point is a compound pendulum, uniform rod. And now imagine a geometry of arbitrary shape. O is this pivot point, and G is this center of mass. Okay. So if I draw the free body diagram of this body, when the line joining the pivot point and the center of mass makes an angle of theta, so you have this set of forces. At G, you have mass times G. At O, you would probably have some reaction force, OX and OY. Okay. And and for a body of finite dimension, for a rigid body, let's say, even if we consider the compound pendulum to be a rigid body, we can write three equations of motion. One involving summation of all the forces in x direction would be mass times acceleration in x direction of the center of mass, hence the bar. Summation of all the forces in y direction is mass times the acceleration of the center of mass in the y direction. And the third equation becomes important if you sum all the moments. So it's a object in 2D, so there are only three equations of motion. Had it been 3D, there would be two more moment equations and one more force equation. Now, when it comes to moment, the moment always has to be about some point. And we choose the pivot point to avoid taking into account OX and OY. And that would be the moment of inertia about O times the angular acceleration. So what is this angular acceleration? This angular acceleration is basically theta double dot. Okay. And what about the moment? Moment about O essentially becomes mg, that is this force, and this is the horizontal distance. Let's say the distance between O and the center of mass is r bar. So it would be mg times r bar, then sine theta. And actually, this moment is kind of a restoring moment. This moment is clockwise and acting opposite to theta, so comes with a negative sign. Okay. So the equation of motion for the compound pendulum, because there is only 1 degree of freedom, which is theta. You see, in this system, you can write 3 equations of motion, but only one of them matters because this object is not free to move in x and y because it is pivoted or pinned at O. It can only perform rotation about O. So only one equation of motion is good enough to describe the motion. And that equation of motion says I0, IO theta double dot plus mg r bar sine theta equals 0. That is the equation of motion. Now the moment of inertia about O is simply the moment of inertia about the center of mass plus m times r bar squared. Okay. Are you familiar to this expression? Parallel axis theorem?
Yes, sir.
हाँ सर.
Okay. In case you have a doubt, so there is O, let's say, and this is, let's say, R of a differential mass. There is a position vector. Okay. And I'm just doing the vector itself. And this is G. So this distance is R bar vector. Okay. And distance between G and this point, this differential mass dm over here, let's call it rho, which is a vector. So vectorically speaking, R is R bar plus rho. And therefore, R dot R, which is basically R squared, is R bar squared plus twice R bar dot rho plus rho squared. Okay. So when I integrate this quantity, to get the mass moment of inertia about O, that becomes, first of all, R bar squared integration dm plus the third term, which is integration rho squared dm, and then this term right here, which is, you see, this R bar is a constant. Although a vector, it's a constant. So I can write twice R bar dot integration rho dm. Okay. Now, if you look at this first expression right here, that basically is integration dm, right? So m R bar squared. This quantity right here is the moment of inertia about the center of mass or center of gravity, which is basically G. because I am using rho squared dm. And in the third case, integration rho dm is basically rho bar times m. That is how we define center of mass. So we take the position vector of a differential mass, we integrate that over the mass. That basically gives me the average position or the location of the center of mass times the mass. Now the irony is, here we are measuring the position of the differential mass with respect to the center of mass itself. So when in the end we get rho bar, that is the position vector of the center of mass with respect to the center of mass. And therefore this rho bar, this quantity right here, is 0. So this quantity goes to 0. Hence, you have the parallel axis theorem. Now, this I bar, the moment of inertia about the center of mass, let that be an unknown. Okay. Actually, in this experiment, we are actually trying to find out this quantity, the moment of inertia about the center of mass. Okay. And it is an unknown. And we could call it m kappa bar squared, where kappa bar is the radius of gyration about the center of mass. Okay. The idea is, if we know this radius of gyration about the center of mass, we can get the mass moment of inertia about the center of mass. Okay. So that makes IO to be m times kappa bar squared plus r bar squared. Okay. So the final equation of motion with linearization. What is linearization? Theta is so small, sine theta tends to theta. So if we talk about the linearized equation of motion, we have theta double dot plus g divided by r bar plus kappa bar squared divided by r bar. Just check, that is the expression that you are getting, times theta equals 0. Okay. When compared with, so this is for compound pendulum. When compared with the simple pendulum, that equation should be g by L times theta equals 0 for simple harmonic motion. Of course, this is a linearized equation of motion, considering theta to be really, really small. Okay. The two equations look very similar. And this quantity for a compound pendulum could be thought of an effective length. Okay. Could be thought of an effective length by comparing this expression with that of simple pendulum, equation of motion of a simple pendulum. Okay. What is the significance of that effective length? So if you have a compound pendulum in hand, okay, but the effective length, this quantity right here, that suggests that your compound pendulum has the same dynamic property, namely the same natural frequency to that of a simple pendulum, whose length, so for a simple pendulum, there is just one length, the length of the string, whose length is essentially this quantity right here. And you might notice that this effective length is not just the distance up to the center of mass. This is not r bar. This is something else from r bar. And actually, here we are talking about an important point in the compound pendulum. Let's call it P, or the center of percussion. Okay. So up to the center of mass, it is R bar. But if you proceed along the same line, the center of percussion lies below the center of gravity or center of mass by how much? Kappa bar squared divided by R bar, which is a positive quantity. So no matter from which side do you hang your compound pendulum, the center of percussion always lies below the center of gravity. So for example, if this one is O1, and if you wish to hang the compound pendulum from O2, then this one is P1 and your P2 would be somewhere over here, always below the center of mass, which also goes to show you that center of percussion is not a fixed point. Okay. Okay, so this is এই পার্টটা কি বোঝা গেল কি বলতে চাইলাম?
হ্যাঁ স্যার বোঝা গেল। স্যার একটা কথা জিজ্ঞেস করছি, ওই কার্পিতে আপনি যে বলছিলেন না, কার্পি যখন পড়াচ্ছিলেন তখন ওখানে বলেছিলেন যে ওই যেই পয়েন্টে গিয়ে ফ্রিকশনটা হয়, মানে যেটা পেন্ডুলামটা যখন বাড়ি মারছি, যেই পয়েন্টটা গিয়ে বাড়ি মারছি সেখানে যে ফ্রিকশনটা, এই পয়েন্টটাকে সেন্টার অফ পারকিউশন বলে, ওরকম বলেছিলেন মনে হচ্ছিল, আমি যতটুকু মনে আছে।
না বলিনি। আর চারপির সঙ্গে এই এক্সপেরিমেন্টটাকে খুলি, চারপির টেস্টটা একবার ভালো করে গিয়ে দেখো। এক নম্বর। দু নম্বর হচ্ছে so in relation to friction in IZOD or Charpy test or any impact test, what I might have said or what any teacher might have said is only something called free swing. That is nothing in relation to center of percussion. It's totally a dynamic property of the system. Okay, so center of percussion. Acha, so here is your assignment question. Okay. Question number 1. Is center of percussion a fixed point? Justify. What is the meaning of the question? The center of mass is a fixed point. No matter from which side do you hang your compound pendulum, the center of mass represents the average location of the differential masses. So integration R dm divided by m. That's what is the location of the, that's what is the center of location of the center of mass. That is the average position of all the differential masses. And no matter on which point do you choose as a center of do you choose as the pivot point, your center of mass doesn't change. Okay, but the center of percussion is not a fixed point. When you hang the object from O1, it would be below the center of mass, and the distance would also depend on the distance from the O1 to G and then the additional distance. Similarly, if you hang it from O2, the distance between O2 and G could be different from O1 and G. Okay, and therefore the R bar from as calculated from O1 may be different from R bar calculated from O2. And also the P2 now lies on the other side, because the center of percussion must always lie below the center of mass. Okay, so the center of the point is the center of percussion depends on the choice of pivot point. Okay, and it would always lie below the center of mass, no matter what configuration do you choose. That means it's the position of the center of percussion keeps on changing depending on your pivot point. Okay, then the next assignment question, that is the third assignment question for the day. That question is, what are the significances of center of percussion? What are the significances of the center of percussion? That is the first part of the question. Which one of these are we employing, or which one of those significances are we employing in our experiment. So I'm about to explain another important property of the center of percussion. Right now, what do we know about center of percussion? The distance from the pivot point to center of percussion serves as the effective length for a compound pendulum. What is an effective length? If the compound pendulum were a simple pendulum, it must have a length equal to the effective length in order to have the same dynamic property. The name of the property is the natural frequency, because as we learned, the natural frequency for the simple pendulum would be square root of G by L, and the same thing for the compound pendulum. Simply by comparing the two equations, we can say it is going to be G divided by L effective, where L effective is this quantity right here. Okay. So this is the significance we just learned about the center of percussion. So the distance from the pivot point to center of percussion serves as the effective length. What is an effective length? An effective length is that, for a compound pendulum, it's that length which a simple pendulum must have in order to have the same natural frequency as the compound pendulum. Okay. Anyways, let's move on to the second property of a center of percussion. So I have my compound pendulum at ease, that is in equilibrium. So it is in its vertical position. So as usual, there is the pivot point and the center of mass. And then I have applied a horizontal force, F, on the body. Okay. Now if I draw the free body diagram, I have the weight, I have the force F, and at O, I'll have the reaction forces OX and OY. Now, of course, I can write, so it was a stationary, and then I applied this force, and that would set the object in motion. And I'm about to write the equations of motion. So there are three equations of motion as we discussed. Now, we would ignore the second equation of motion. Okay, let's just consider the first one, which tells us that OX minus F equals M times, of course, this one is AX bar, AX bar. And the moment about O, because this time the weight passes through O, so the moment is only due to F. So this equation, so you are ignoring this equation, the second equation, but first and third are we using. This is what we get out of first equation. The third equation tells us, let's say this much is R bar and this much is X. So, no, let's just make this distance along the axis as X. So F times X, or X times F, is the moment due to O, and that's a negative moment, right? Clockwise. So it is M times R bar squared plus kappa bar squared, which is basically IO, times theta double dot. Okay. And you need to realize that AX is also a theta. In this configuration, AX is also a theta. and A theta is simply r bar, A bar theta is simply r bar theta double dot, if I consider this object to be a rigid body. Okay, so what do we have here? R bar theta double dot, and the expression for theta double dot is so you substitute that expression. So M cancels out. Okay. So this is the expression for OX now, the horizontal reaction at the pivot point. So it is F 1 minus X F R bar squared, sorry, R bar plus kappa bar squared divided by R bar. Now, if I choose X equals R bar plus kappa bar squared divided by R bar, or in other words, if I apply that horizontal force, no matter what magnitude, that could be 10,000 Newton. But if I apply that while it is in equilibrium at the center of percussion, this OX becomes 0. So the horizontal reaction becomes 0. Of course, the pendulum will oscillate. Pendulum will have some finite non-zero acceleration. That is true because theta double dot is non-zero. But the horizontal reaction at the pivot point becomes 0. Now this is an important result. So whenever a batsman in either cricket or baseball is hitting a ball with the bat, okay, or in any other game, when they are trying to hit a ball with a racket or a bat, if they want the object to go furthest with very little effort from the wrist, they would try to hit the object with the center of percussion. So essentially their wrist act like a pivot point, and they don't want their wrist to be damaged, right? They don't want their wrist to be harmed. So they would want minimum reaction at their wrist. So in order to do that, they would try to hit the object, the ball, with the center of percussion. Okay. So this is another significance of the center of percussion, that if you apply a horizontal force in the equilibrium configuration of the pendulum, there is no horizontal reaction at the pivot point. Okay, but this one we are not using in today's experiment. So the last assignment question was, what were the different significance of center of percussion? We just discussed two, and the second part of that question was, which one did we employ in our experiment? The answer to that is the first part. Okay, এই পার্টটা কি বোঝা গেল? আমার কথা শোনা যাচ্ছে?
শুনে
এই পার্টটা কি বোঝা গেল?
আমার স্যার একবার দেখতে হবে স্যার, এই ঘটনা আবার হেজি হয়ে গেল।
কোন জায়গাটা বুঝতে অসুবিধা হচ্ছে বলো? এনিওয়েজ,
এখানে একবার তখন প্রবলেম না, একবার ফোন করবো স্যার, অসুবিধা নেই তো স্যার?
আমার মনে হয় তোমরা যদি টেক্সট বইটা দেখো তারপরে এই ভিডিওটা দেখো, কারণ I don't have any other thing to contribute. You can actually go through the textbook. Okay, so that should suffice. And revisit the video, then that should help. Anyways, we are only going to use the first property that we learned to do the mathematical part of the experiment. So remember what we did. We had configuration 1 and configuration 2 for the compound pendulum, and for which we note down the time taken for 10 oscillations. This is for first configuration, the time period times 10. And this is for the second configuration. We had noted down the time period for 10 oscillations. From that, you would get the time period for the first single oscillation in each configuration. From that, you will get the natural frequency, which is twice pi divided by the time period. So this one would be omega 1, and omega 2 would be twice pi divided by T2. Okay. Now we already know. So this part we would get from the experiment. So from experiment, we can directly get the time period and the natural frequencies. And once we have the natural frequencies for either configuration, we can find out the square of the natural frequencies. And as we have learned, omega 1 squared is r bar, equal G divided by r bar 1 plus kappa bar squared divided by r bar 1. See, the mass moment of inertia about the center of mass is a constant. It is irrespective of the configuration. It's the location of the center of mass that is changing depending on the configuration. The radius of gyration, it would not change. R2 bar plus kappa bar squared divided by R2 bar. Now there are three unknown quantities: R1 bar, R2 bar, and kappa bar squared. Okay. So two equations will not suffice. But then we also have the third equation, R1 bar plus R2 bar. If O1 was the first pivot point and O2 was the second pivot point, okay. So this distance, let's say that is L. So that is actually the sum of R1 bar plus R2 bar. To get this capital L, all you have to do is to take your compound pendulum and measure this distance using a tape or maybe a scale, whatever you choose, to get this L. Okay. Achha. Now I would rewrite. So these are three equations for three unknowns, and that's how we are going to solve them. So we'll rewrite these equations: R1 bar plus kappa bar squared divided by R1 bar equals G divided by omega 1 squared. Okay. And R2 bar plus kappa bar squared divided by R2 bar, G divided by omega 2 squared. I would call this one as C1 and this one as C2. Once we calculate these, those would be C1 and C2. Okay. Now I would multiply the first equation with R1. So C1 and C2 are known quantities, by the way. So C1 times R1 bar is R1 bar squared plus kappa bar squared, and R2 bar, similarly from the second equation I have kappa bar squared equals C2 R2 bar. Now we will subtract each of these expressions. So these two will cancel out. So here I have R1 bar plus R2 bar, R1 bar minus R2 bar equals C1 R1 bar minus C2 R2 bar. C1 and C2 would be different. But then we can use a third equation to write this R1 bar plus R2 bar as L. and that would be a linear equation in R1 bar and R2 bar. Or in other words, L minus C1 times R1 bar equals L minus C2 times R2 bar, which would basically give us a ratio R1 bar by R2 bar equals gamma, where gamma is this quantity, L minus C2, L minus C1. Now, if I substitute this expression to the third equation, so gamma plus 1 times R2 bar equals L. From that, I can get R2 equals L divided by 1 plus gamma. Once I have R2, I can get R1 using this equation. Let's call it the fourth equation. Once I have gamma R1 bar from the fourth equation, okay, I can actually substitute that. Actually, I don't even need gamma, need R1 bar. Once I have R2 bar, I can substitute that to equation number 2. So basically this equation, okay, to calculate. So this C2 is a known quantity, R2 bar is a known quantity. I can get kappa bar squared as C2 R2 bar minus R2 bar squared, where C2 is basically the acceleration due to gravity divided by the second natural frequency square, okay, which we have already calculated. So in this way, we can get the radius of gyration, okay, of the connecting rod about the center of mass. So it is the radius of gyration about G. How do I get the mass moment of inertia? Simply by multiplying kappa bar squared with m would give us I bar. That's all we need to do in this experiment. এই পার্টটা কি বোঝা গেল?
হ্যাঁ স্যার, এটা বোঝা গেছে।
connecting rod
এবার তোমরা এক্সপেরিমেন্টের ভিডিওটা দেখো, ওকে, তোমরা পুরোটা দেখে নাও, তারপর রিলেটেড টু থিওরি বা এক্সপেরিমেন্ট তোমাদের যদি কোনো কোশ্চেন থাকে, I will try to answer once we are done with this video.
of an IC engine, and you know this is the small end and this is the big end. This goes to the piston side and this goes to the crankshaft side. So here we will make an attempt to find out the moment of inertia of this connecting rod using this experiment. So here the following dimensions we will be using. So see, this is the knife edge from which we will suspend this. So now you can check the drawing. So this point is O1. This will be required for your calculations. This is O1 and center of the small end is A. The center of mass is G and the center of this big hole is B, and this from this point where we will suspend the connecting rod is O2. So this is the line O1 A G B O2, and from 1 to O2 the length is E, which we'll call, and from G to O2 to G it's C2, and O1 to G it's C1. And from the center of the small end to the mass center is A. So what we'll be doing here, so we'll first suspend it from the smaller end, and we will check that whether it's perfectly vertical or not. We'll determine the plumb line using this weight. Okay. So now it's vertical. Now what we will do is, we will just measure its time period. Just we will give a small angular departure from the vertical line, and then we'll leave it on its own and it will vibrate, and we are interested in finding out the period of vibration. But we will, since the period of vibration is small and it's difficult to measure, we will measure time period of 10 oscillations. We will measure the time period of 10 oscillations using stopwatch. Then we will suspend it from the big end. Then we will again measure the time period of 10 oscillations. The first one we will call T1, and the second one we will call T2. It's T2 I think. So
T2 is a Gyration and smaller.
oscillations, this is for one oscillation when it is suspended from the small end. And now if you suspend it from the big end, so this is the time period of 10 oscillations, and this is time period of a single oscillation. That means simply you have to divide the reading by 10. Okay. And from that we will find out the length. This length is actually the length from the point of suspension to the center of percussion. So these two lengths are required. So if you suspend it from here, the center of percussion length from here, we do not know where the center of percussion is, but from this period we can find out from this end, center of percussion will be somewhere here, which you can find out from this reading. And when you suspend it from the other end, then you can find out what would be the corresponding distance of the center of percussion from the point of suspension. Now he will measure the time period of 10 oscillations using his stopwatch, mobile stopwatch maybe.
Yes, sir.
ওয়ান স্টার্ট বললে স্টার্ট করে দেবে, 10 বললে স্টপ করবে।
স্টার্ট করবে আবার?
না না, আমি স্টার্ট বললে স্টার্ট করবে।
ঠিক আছে।
স্টার্ট 5 6 7 8 9 10 8.42 সেকেন্ড 8.42 সেকেন্ড। হ্যাঁ, রিসেট করে নাও। স্টার্ট 1 2 3 4 5 6 7 8 9 10 8.05 ready start 1 2 3 4 5 6 7 8 9 10 8.11 second complete.
Now next, now it will be suspended from the big end.
রিসেট করে দেবো। এটা সেম প্রসিডিউর তো।
The procedure is same, just like before.
ওকে স্যার।
No.
Start. 1, 2, 3, 4, 5, 6, 7, 8, 9. Ready? Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 7.79 second. 7.797. Next. Ready? Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 7.67. 7.67. Next. Ready? Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 7.52. 7.52. No, sir, আলাদা আলাদা calculation.
Oh, another calculation.
Sir, বলে দিন।
So now for this one has to be divided by 10 and taken here, divided by 10 here, divided by 10 here, and from that you find out three values of this L1, and from here similar process, so three values of L2. Right? The তিনটে calculate. A small error. So this would be this F would be not L1 plus L2 by E1, it would be L1 plus L2 by E minus 1. And other things are okay. So now what are these? C1, C2, A, KG, IG. So L1 and L2 are the values what we are getting from here, L1 and L2, what we will get from calculations. So for here you are getting three values. So observation number 1, so you made three observations. So for both the cases, so 1, 2, 3. So for observation number 1, you first find out F. F is L1 plus L2 by E. What is E? E is the total length from O1 to O2. So that dimension is given here. So if it is not given, we will give you, oh no, you can calculate it from here. The length between the centers, so length between the centers, that means from here to here, or from the length between centers from here to here is given, that is 17.65, and the bore of the small end, this bore is given, this is D1 and this bore is D2. So once you get the bore diameter, you can find out what is E. So this is diameter by 2, this is given, center to center distance is 17.65 plus another diameter by 2, so you get E. So that you call E. So this E is used here. Then C1. C1 is from here to the center of mass, and this is C2. C1 is not known to, but known to you now. C1 you have to calculate using this relation. C1 is from O1 to the center of mass. Here it is written, C1 is, this is E, E is O1, O2. O1, O2 is E, that we already know, and C1 is O1G. O1G means, I can do that. This center, this O1, this point of suspension, to G. This is C1. And C2 is from this point of suspension to center of mass. So these values you can calculate using these relations. And distance of G from small end center. Okay. Now using, you have got these relations C1 and you have got this values of C1 and C2. So once you locate the center of mass, C1 and C2 you find out means you have located the position of the center of mass. Then what is important is from the center to the center of mass, small end center to the center of mass, and that is C1 minus D1 by 2. And if you want to find out the moment of inertia about this center of mass, that is Ig, and that is kg, and this kg is the radius of gyration corresponding to Ig. Ig is the center of moment of inertia about the center of mass, and kg is the corresponding radius of gyration. So that is C1, C2, F is this one is C1, this one is C2, root over. So you now know all the values. You find out kg, and moment of inertia Ig is, the mass is given. The mass is given, so m multiplied by kg square. So this is m multiplied by kg over so in kg meter square, because mass unit kg and kg is in meter, so kg meter square. This is your Ig. And if you suspend from A, if you by some means you cannot suspend it from A, but if you suspend it from A, then your center of just like this, the distance of center of percussion is kg square by C1 plus C1. So where C1 is the distance of the center of mass from the point of suspension. So if it is suspended from the center, then your center of percussion distance would be A plus kg square by E. So you have, after you finish off these calculations, then you have to answer these questions. Okay.
ওকে, কোনো কোশ্চেন রিগার্ডিং দ্য এক্সপেরিমেন্ট বা থিওরি, কোনো কিছু নিয়ে কোনো কোশ্চেন যদি আছে তো বলো।
স্যার লাস্টে স্যার কয়েকটা কোশ্চেন করতে বললেন,
বলো।
দেখলাম ওইগুলো মানে ওই কোশ্চেনগুলো জিনিস আপনি যে থিওরি বই থেকে বলছেন ওখান থেকে মোটামুটি আইডিয়া পাওয়া যাবে।
হ্যাঁ, থিওরি থেকে ওখান থেকে তো পাওয়া যাবে। মানে ইনস্ট্রাকশন শিটে যে কোশ্চেন সেটা বলছো, সেটা তো আমার ধারণা যে থিওরি ডিসকাস করা হয়েছে সেটা কি করা যাবে।
না যেটা ইনস্ট্রাকশন শিটের মধ্যে ছিল অনেকগুলো কোশ্চেন বললেন যে এখানে করতে হবে বললেন লাস্টে।
ও আমি যেগুলো বললাম সেগুলো মোটামুটি ক্লাসে ডিসকাস করাই হয়েছে। আর হ্যাঁ, বাকি যদি হেল্প লাগে তাহলে থিওরির জন্য টেক্সট বই দেখতে পারো, ঠিক আছে। ডায়নামিক্স অফ রিজিড বডি তোমাদের কি কভার হয়েছে? হয়ে যাওয়ার কথা, এই সময় অবধি হয়ে যাওয়ার কথা। যেমনটা মানে ডেতেও থার্ড ইয়ার ফার্স্ট সেমিস্টারে হয়ে যায়, সেটা তোমাদের এই সেমিস্টারে হওয়ার কথা। তো সেখান থেকেই এই ডিটেলগুলো পাওয়ার কথা, না হলেও টেক্সট বইতে তোমরা পেয়ে যাবে। ওকে,
প্রশ্ন থাকলে আপনাকে ওই চ্যাট বক্সের মধ্যে জানিয়ে দেবো, যেরকম জানিয়েছি।
হ্যাঁ জানিয়ে দেবো, ঠিক আছে।
থ্যাংক ইউ স্যার।